This video just explains some of the very basic things about internal flow and what some of the considerations are, right? So the two things we kind of led off with in class were that for internal flow, right, we need to ask ourselves both, is the flow laminar or turbulent? Okay. And second question, is the flow developing or fully developed? And this should be reflected in that Nusselt number correlation sheet that you have, right? You ask first question first, second question second, etc. Right? So let's then take a look at what the criteria are. All right, first of all, okay, to determine if it's laminar or turbulent, okay, I need to solve for my Reynolds number, which is based on my diameter. Okay, so in this case, it's equal to my free stream velocity. Okay, that's this here, times my diameter over my kinematic viscosity. Okay. This diameter here, okay, is the diameter of the inner part of your pipe, okay, or if it's a non-circular cross-section, this becomes your hydraulic diameter, which is equal to 4 times the cross-sectional area of that cross-section, right, divided by its perimeter. Okay. Now, our critical Reynolds number is equal to 2300, meaning that for Reynolds numbers less than 2300, we have laminar flow. Okay, and for Reynolds numbers greater than or equal to 2300, we have turbulent flow. Okay. Second question we ask is the flow developing or is it developed? All right, so to answer this question, we actually need to solve for the location where the boundary layers meet, either hydrodynamically, H, or thermally, T. To do that for internal flow, okay, solve for the hydrodynamic location where the boundary layers meet, or hydrodynamic boundary layers meet, okay, we set this location equal to 0.05 times your Reynolds number times your diameter. Okay? And for your thermal boundary layers, okay, the location where they meet is equal to 0.05 times your Reynolds number times your Prandtl number times your diameter d, right? Where this is your inner diameter here of your tube. Okay. And so if the total length, let's say that this is the total length of your pipe, okay, if your length is greater than 10 times either your hydrodynamic or your thermal boundary layer, then you can consider the flow to be fully developed. Okay. If it's not, if your length is less than either of these, then you've got developing flow. And you'll run into two cases. Case 1 is where you have both locations here are developing. We call that a combined entry length problem. And 2, you have the case where your thermal boundary layers have not converged until fairly far downstream, but your velocity boundary layers converge rather quickly, right? And so this is called a thermal entry length problem. Okay, so this allows you to determine virtually everything you need to understand which Nusselt number you have to use to solve for things like how much heat is getting into that moving fluid, right? But these are really steps 1 and 2. Okay. One other thing that needs to be understood here is that we need to define sort of mean temperatures, right? What you can see here is that at any location, let's say that this is our location here, the magnitude of the temperatures at the location are represented by these arrows, right? So if our temperature is varying in the radial direction, then we need to be able to define a mean temperature. And so what we usually use are mean temperatures at the outlet and mean temperatures at the inlet. Okay, and that allows us to solve for the amount of heat that's been transferred by convection in our system using a first law energy balance, right? So the heat transferred by convection is equal to our mass flow rate times our heat capacity times the mean outlet temperature minus the mean inlet temperature. And that's how much we're heating our water up. Okay. We can also relate this to a convection coefficient, right? In this case, if it's the heat transferred by the entire length of the pipe into all of the moving fluid, then it's related to some average convection coefficient. Okay, and what we need to do is we need to use Nusselt numbers to come up with this and to try and determine what temperature difference we're going to use here for both constant heat flux and constant temperature boundary conditions. Okay, this is what we're going to spend the next couple of videos taking a look at. But if you understand sort of how to approach these two questions and what's going on in here, in addition to sort of these locations for developed and developing flow, you're in good shape to move on.